Sorry. All right, don't want that. So it's probably worthwhile. I realize it's in German, but that's fine. The Francis turbine. Even better.
Francis turbines are often used in pumped storage plants to create electricity. The generator, which produces electricity, is connected through a shaft to the runner of the turbine. The runner is composed of runner vanes that are curved. The guide wheel surrounds the runner. The setting angle of the guide vanes can be adjusted to meet fluctuating power demands or to cause the turbine to spin at a constant speed at changing watt levels. A volute casing surrounds the guide wheel. Water enters the turbine from a pipe connected to the higher reservoir of the pumped storage plant. The water is then conveyed through another pipe to the lower reservoir. The water flows through the turbine, causing the runner and, consequently, the rotor of the generator to spin and to produce electricity.
Okay. What else we got? We saw this before. So that's a similar process to the Francis turbine we just looked at. Maybe a bit more obvious as to what's going on is that you're blowing a jet of air, in this case, onto these little cups, and as a result of that, this thing whisks around. And so if you imagine this Pelton wheel, as it's referred to, with all these little cups on it, actually being so large in diameter or radius that it's basically a horizontal shot, it actually starts looking a bit like the examples we were talking about, squirting water at a trolley that's able to move along the ground. And so what I wanted to do today was finish up talking about what we were interested in, and this is just interesting as well, is to finish up talking about, I'm going to turn this down and talk over it, is to kind of make the connection between what we've talked about in terms of conservation of linear momentum, transferring momentum from the fluid onto the solid structure by moving it, ostensibly in a straight line for what we've talked about before, but it's not much of a stretch to be able to take that and to be able to, instead of looking at moving in a straight line, to have something that deviates from a straight line and goes around in circular motion to convert linear momentum into rotational energy, which is, of course, the crux of wind turbines, hydropower turbines, gas turbines using steam that's generated from coal, or gases that are generated burning natural gas, and to be able to turn that into electricity as just one example of this. So it's an important concept for us to be able to understand. And this is not generating any power at all, but it's just these vanes that go into the water, the little aluminum vanes that get pushed around, and an Archimedes screw, which is this almost concentric circle of the pipe that allows you to pump water from a lower elevation to a higher elevation. So obviously it's doing work. It's taking fluid from the lower river to a pond that's higher than it, you can see that, and it's using the conversion of momentum of the river water to be able to provide the power to be able to do that. And so that's what I'd like to attempt to do today. So that's the plan for today. Oops, I didn't mean to do that. All right. So, what I thought we would do first is talk a little bit about linear momentum, just to try and make sure that there are no confusion about what we've done so far. And I see my little pad here is flashing red light, so I guess that's what your battery is low means on this. Where are we? %, full. That'll get us through today. That's fine. And so let's just go back through track. So these are two things today. Talking about linear momentum, and then talk about rotational momentum or moment of momentum equations. So the first part is to just maybe backtrack over what we talked about so far. And I'm just going to draw our little device that we've talked about so far, that sits on a trolley. And it's easiest for us to define the relative velocities of fluids coming in and departing, for instance. We could have a force that's applied against this. We can make the case that the coordinate system that we deal with has to be a Cartesian one for what we're interested in. And I suppose these would also have attached to them appropriate areas of the impinging flow that comes into this. And so, in addition to this, what's important is that we can define, for instance, a velocity w, and I suppose in the way we've done it before, we could define a velocity of the control surface, so that when we look at the total length of these, that this is the velocity of the static jet. So it's the boat thing we've used. Fireboat goes at 1 meter a second, squirting out forward at 1 meter a second. To a static observer, the water is traveling at 2 meters a second. So this is just a consequence of this. And so from this, we had two basic expressions. The first is obviously from this term here. The static velocity is equal to the sum of the relative velocity relative to the control volume and the velocity of the control surface. Not control volume, but control surface, because we're not allowing that to deform. So actually they're the same. So we could use either term. So that's the first thing that we need to deal with. The other term that we need to deal with is the conservation equation, which we've tended to write as something like this. It's in three directions, but let's just choose one component. Forces in the x direction are equal to the relative velocity, again in the x direction, the velocity of the control surface, again in the x direction, and multiplied by the mass flow rate. So that's the full set of equations that you'll need in this class. I guess we might also note that when we're talking about mass flow rates, we can also define them as areas times density times the relative velocities, the velocity relative to the control surface. So this is absolute as well. And so this is the way that we define the mass flow rates. So together, if you like, and including this mass flow rate term, these are the two expressions, or the three expressions when you pull in this, that define our system. And so this is the correct expression. Because you'll see a variety of different expressions used in the book, and we've used a variety of different expressions which are based on this, but are decompositions, I guess, subsets of this behavior. And so you might remember that we looked at, in terms of this trolley, maybe three different things. one where the trolley's static, not moving, one where it's on wheels and is able to move, and one for the gas cylinder where we don't satisfy this condition of steady state. And so those three conditions, maybe we can just write out and look at what this expression might look like. So the first one is static and steady state. So steady state means that just for this little geometry, that the fluid that comes into the control volume doesn't accumulate inside the control volume, it goes out. That's been the case for all of the systems we've done except for one, which is the gas bottle. So everything we've done is steady state. So static, by definition, means the velocity of the control surface is equal to 0. And steady state, by definition, means that the sum of the mass flow rates are equal to 0. Mass flow rate in equals mass flow rate out. It doesn't have to be just two components, but could be out of all kinds of holes. So if we do that, and we take this expression, then we can write that as the sum of forces in the x direction are equal to the relative velocity, the velocity of the control surface, again both in this direction, and the mass flow rate. We've said that because this is the case, it's not moving, it's anchored, then by definition we lose this. And as a result of this, this also could also be written as, if this is 0, then W has to equal the static velocity. So this could also be written as, the static velocity times the mass flow rate. And of course, since the thing isn't moving, the relative velocity relative to the system is the same as the static velocities of it coming out of it. So that's the first of our conditions. And you could also solve it using this, as long as you just throw away the right terms. The second one, is for a moving control volume, which is what we did last time, but again steady state. And so moving means that the control surface is now not equal to 0. But again, because it's steady state, there's no accumulation within our vane, V-A-N-E. And so if that's the case, then we might write this out in some way as, just as we have above, sum of the forces in the x direction are equal to this. This no longer is 0. And so we need to know each of these magnitudes. And so what we could realize is that if we write it out a little further by expanding this, I'm not doing anything else other than just rewriting this. And if we define mass flow rate in terms of how we've defined it before, we can do it in blue, I suppose. So mass flow rate is equal to the cross-sectional area of flow times the density of the fluid times the relative velocity. And again, this is the summation, I suppose we should put in here. And it is here. So these are all summations of these. And so what we could do is we know that the static velocity is equal to the velocity relative to the control surface plus the control surface. We could write this as W is equal to Vs static minus the control surface, right? Just by taking this off to the left-hand side. And if we then place this in here, for each one of these, we have that the sum of the forces in the x direction is equal to the summation. What's this going to be? This is going to be the static velocity minus the velocity of the control surface plus the velocity of the control surface. And I guarantee this has a point in what we're doing here. And again, this will be static minus control surface. And so the importance of doing this is that now we realize that these two terms cancel out, and that the force that's applied, or the sum of the forces, have to balance to how fast the control surface is going, multiplied by area, density, and the difference between the static jet coming in minus the velocity of the control surface. And so that might seem a little esoteric, but we made the point before that there are really two conditions. Condition one, and that is the velocity of the control surface goes to 0. And if that's the case, we can calculate the force, and I suppose the force would be equal to VCS multiplied by A times rho times VS. Oops, I did the wrong one, so this is wrong, right? Didn't catch me on this. I was wondering why it actually is a strange result. It's not. I'll just score it out. So VCS minus VCS gets rid of these two, and it's this one that's left. So this term here is VS. Okay. Otherwise, this doesn't make sense. VS minus VCS. And so what this says is that if the control surface is static, then this term here is equal to 0, and then this will just be equal to Vs squared rho times A. So it's a finite number. The second condition is if the force is equal to 0. So you can either hold the thing there and you get a maximum force, and the maximum force is this magnitude here, or you can allow it to run, in which case the force is 0. And if that is the case, this can only be 0 if these two terms are equal to each other. So this has to be that the velocity of the control surface is equal to the velocity of the static jet. So physically that means that the fluid that's coming in and hitting it here, the vane has to be going at exactly the same speed for it to have no force retarding it. And those are the two end-member conditions. This expression, of course, that we have here is true for all conditions between that. And that's useful because we could actually think about drawing a graph that looks like this. That, for instance, looks at the velocity of the control surface versus the force that's applied. And so this would be 0. This would be V static. And what we've just said is that if the velocity of the control surface is 0, then the magnitude of the force is a maximum, which is this. Doesn't matter what these are. So this is one data point that we have when the velocity is 0. When the velocity is 0. If the velocity of the control surface, if the force is equal to 0, then the limiting value is that the control surface is moving exactly at the speed of the jet that's coming into it, and that's this point here. And so this defines it's not a straight line because it's a square term, but it's a line that connects those two, and it looks like something in between. And so this would be this expression here, plotted for different values of CS. And the reason that's important is that we know that power, let's do it first. Work is equal to force times displacement. Okay. Work has some mass, I move it up, I'm doing work on it. The work that I do is the weight of this multiplied by the distance it goes. Power is rate of doing work, so it's force times displacement over time, which is the same as force times velocity. So power is watts, so we could also write that power is equal to force times velocity. So if you take this expression, you see there are two end members. We could plot the magnitudes of power related to each of these control volume velocities. And so we know that at zero velocity, the velocity is zero, but there's a big force. But although there's a big force, there's zero power because the product of this is zero. So we have one point here, which is zero. We know that when it's at maximum velocity, the force is zero. So we know the product here is also zero. And so if we look at intermediate points, where the magnitude of the force and the control surface velocity is intermediate, then it's going to look like this. And so basically this is power. So you can't generate any useful work if you're pushing against something that's not moving. And you can't generate any work if something is moving quite quickly and there's no reaction against it. There's some intermediate position in there where you get the maximum power. And you could plot this equation. You could plot, this is just the product, force times VCS. So you could do that calculation. And you see it. And so that's really the principle by which many systems work. Okay? So let's track back. We said we'd talk about three different systems. One is static, steady state. One is moving and steady state, mass in equals mass out. And we said that we could use this expression in all cases, and it was just, we'd end up with a degenerate form of it if we made those certain assumptions. The final one that I want to do, and I don't want to, let's see, I run out of space. I guess I could go back and just do this. The final one that we might do, since I can do it, would be number 3. And number 3 was moving and non-steady state. And of course, in my parlance, that is the decapitated gas cylinder, which we've seen a few times, right? This is Fx. We need our coordinate system, x and z. And we did talk about this last time. But the conditions for this are moving. So the condition is the velocity of the control surface is not equal to 0. And non-steady means that the sum of the mass flow rates is not equal to 0. And that's because we start with a mass in here, and mass flows out of it, and so the mass is decreasing with time. And so if you have a control volume that includes this, the mass is not conserved. And so what we can also do is we can use this same expression that we had before. Sum of forces in the x direction are equal to the velocity relative to the control surface, which of course is this velocity out of here, if it's driven by the pressure inside, plus the velocity of the control surface, multiplied by the mass flow rate. Again, this is in the x direction. And that's a pretty easy one to be able to look at. We can look at those two end member conditions. So static, by definition, velocity of the control surface is equal to 0. If the velocity of the control surface is equal to 0, then the force that's applied has to be W1 times the mass flow rate. W1 is in the positive x direction here. Mass flow rate is out, so both of these terms have to be positive, so the force has to be in the positive f direction. So to hold it in place, once we've drawn this control volume around this system here, to hold it in place, we have to push in the positive x direction, which of course we're resisting the thing pushing back against us, right? So that's the one case. If we look at the other end member case, the force goes to 0. So we could put any force we like on it, but if we put the force in the x direction equal to 0, then the only way we can get that is if the velocity Wx is equal to minus velocity of the control surface. Right? This term here. This is always finite. There's stuff coming out of here. It might not be moving, or it could be moving, but it's coming out of here. So this is finite, but the only way it can equal 0 is if these are balanced with each other. So this says that it comes out at some velocity w, and this is a negative value, so it means that the control surface is physically going to your left, I guess, my left and your left. And those are the two end member behaviors. And so the force is positive, and it's pushing to the right here, and this is negative, and it's pushing to the other direction. So I just have to be consistent. So my point really was just to make the case that all of these expressions that may seem kind of random and a bit different, really the important expression is this. It always applies, and always true is that static velocity is equal to the sum of these other two. I won't underline them. And we have three equations from this, but typically you only need to deal with one direction, maybe two. There is an example, which I won't go through, in the notes. I guess it's here. If I go back to this. And you can go back to some of the other videos to look at it. The same idea of using a moving vane. In the book, they use exactly this expression here to be able to solve the system equation, relative velocities. But the reason they do that all boils down to the rationale that we've just talked about for these past three cases. And so sort that out in your mind, because it actually does conform to the same behavior. All right? So you can look at one of the previous year's movies to look at that. All right, what am I going to do now? I'm going to get rid of this since this is all recorded. And I'm going to start back on this sheet. And what we're going to do is we're going to talk about the idea of this Pelton wheel. So let's look at it again. Just I think kind of a neat deal. So you can imagine from what we said squirting something at a thing on wheels and moving it is kind of a bit like this. It just happens to this licks around in a radius. But you could imagine that the expressions that we use are perhaps quite similar. One thing that's a bit different about this from the sprinkler problem, think of a Gardner sprinkler with fluid coming up through the middle and going out to the side, is that the jet isn't impinging on the outside of this, it's coming from the inside and squirting out, a bit like the Francis turbine that we looked at the beginning of class in that first movie. And so what I want to do is talk about the rationale of how we can move from what we've talked about for conservation of linear momentum to talk about rotational momentum or moment of momentum. And the big picture is actually quite straightforward. And in the simplest case, if we ignore cross products and the need to do random cross products, what we could do is with this expression, which we can write out as we have before. What we could think about working with would be our trolley system, which I'm going to draw upside down. Where water comes in here at some velocity W1 and goes out here at some relative to this thing velocity W2. We think about applying a force to this to hold it in place, F, and I'm going to call it F theta. And what colors do I want? And we draw something here that looks like this, that has some radius attached to it. So this is a fulcrum that this is circling around. And do I need anything else? I guess I'm going to call this could possibly also be called W theta. And this also gets defined with some angle theta and some rotational velocity omega. So hopefully you can see that this little trolley that we have here is actually not very different. It's flipped upside down. It doesn't have rollers on the underside of it, but we have something coming in and it's getting squirted out through the system. What we could do, we could take this expression here and we could just multiply both sides by a radius, not violating anything. It's just we're choosing to multiply it by a radius. If we do this, then all of a sudden this becomes a torque, and this term becomes a term that looks at rotational accelerations around the system. And so what we could do is we can now use this to be able to figure out exactly what the rotational equilibrium equation is here. And it's this expression here. It's written out in a kind of complicated form from Reynolds transport theorem. We don't need to worry about this. These are cross products for looking at, because this is a vector and this is a vector also. But if we write it out in shorthand, we could write it out something that looks like this. Or I think I'd prefer to write it out in this way, which is just that a radius multiplied by relative to the control volume velocity plus the velocity of the control surface multiplied by the mass flow rate is equal to the torque. This torque is just the product of a force and a lever arm. And it's useful for us in being able to do work. This magnitude of the mass flow rate is going to be equal to some cross-sectional area, a density, and a velocity, normal to the control system. And I guess we should know that in terms of conversions, 2 pi radians a second is equal to 1 revolution per second. And we can also write the fact that velocities in this direction, theta, are equal to the radius multiplied by rotational speed. Right? So this is the the angular velocity. And it's in radians a second. So we can always make those things. And I guess while we're at it, why not just close this out? We can also use this to calculate the power in the system, which is equal to the torque multiplied by the rotational speed. So this, if you like, is directly analogous to the linear system where the power is equal to force times VCS. This is the rotational velocity, angular velocity, and also the torque. So it's directly analogous to that. And so what we can do now is we can use this to be able to calculate, for instance, what the power would be for some kind of system. So what we might do is look at an example that uses this. We can avoid all this. You can look at the dot products if you want. You can do these derivations. But look at basically an example that attempts to do this. The epitome of which is a sprinkler. It's slightly different from our other system because the mass that's coming up through here, well, it's at 90 degrees, and so it doesn't have any influence when we resolve this. But the mass in this system is actually constrained. And so it's actually a steady system. The amount that's flowing through into the system is the amount that's flowing out of the system. When you look at these rotational behaviors, it's not very important for us, but in the same way that we used a right-hand rule for the Cartesian system, x, y, and z, the right-hand rule for rotational systems is an axis of rotation, and then your fingers are the positive direction around that. So it matters whether you're going clockwise or counterclockwise. Actually, the direction for us isn't going to make any difference. Some more derivations, blah, blah, blah. And this is the example. Let's work through an example. And so I'm not going to do it on top of this. I'm going to write it out in full because it's a relatively straightforward example. The idea is that you have water coming up through and into this disc. This disc has 3 nozzles that come out of it. They distribute the fluid that comes out of here, and they kick it at some angle relative to the tangent to the rotation. This angle is theta. And we'd like to be able to figure out 2 conditions. And they're worked here, so you can go back to it. But the 2 conditions are, one, if you're holding the disc static and it doesn't move, what is the force that you have to apply to hold it in place? If you let it go and release it, what is the velocity of the plate as it spins around? So those are the 2 end member conditions. And of course, you could look at the whole spectrum of things. If you specify a velocity of the control surface, you could work out what the torque is that you'd have to apply. Just like in the case of the gas cylinder. Hold it in place, what force do you have to apply for the given velocity? If you release it, what velocity does it take? It takes the velocity of the gas coming out of the system. So if we go back to that, let me draw it out here. So we have some expressions here. Let me do this. So what do we have? We have this. We have a jet coming out of here. We have a line which is a tangent to this here, and this is some angle theta. We have 3 of these, all doing the same thing. And I guess I'll draw it on its side just so we can see it that way. And we have some flow rate coming in, which is Q. And we know it comes here and then goes out through here. We know that this radius is R. And we know that we have some positive direction of rotation defined. So I suppose we could write in these as W2 W2 and W2. And then we could start trying to solve for these two cases. The first one if it's held in place, and the second one if it's allowed to rotate. So what do we want to write out? So we want to use this expression here. So the torque that we have to apply is equal to the radius multiplied by the velocity relative to the control system. I guess we'll call that theta, plus the velocity of the control surface, which is also theta, multiplied by the mass flow rate, which is density times the area of these nozzles, multiplied by the normal velocity. And so we have to figure out exactly what these are. So if we look at what's going into this system, then W, actually mass flow rate. So the mass flow rate is going to be equal to Q times rho. And so the mass flow rate coming out for a single jet, if you like, just do one of them. So we'll talk about just one of these. Is going to be equal to what? This is going to be equal to Q rho over 3, because it's coming out of here, and it's coming out of here, it's coming out of here. And for conservation of mass means that this total amount has to be divided by 3. So we have that. We have the velocity of the control surface. And we want the velocity coming out of the system in the direction that's tangential, which is W theta, W2 theta, I guess. So this is going to be equal to what? It's going to be equal to this mass flow rate. So W2 theta is equal to the volumetric flow rate divided by the area. So this will have, the nozzle will have an area 2. So hopefully that's right. This is a volumetric flow rate, meters cubed per second, divided by an area, which is meters per second. So this is a velocity. This is going to be the velocity in the direction W2, and so what we have to do is correct it for the magnitude which is in this direction. And so this is going to be W2 cosine theta, because this angle here is theta. And this is going to be times cosine theta. So this is for one nozzle, and this is for one nozzle. So I guess we could clean that up a little bit by writing it out again. T theta for one nozzle is going to be equal to the radius multiplied by Q3. Yeah, actually, let's not do it that way. Let's do it because it becomes more transparent if we do it this way. So I haven't changed it very much, but I will note the fact that this term is the term that goes in here, and VCS is the term that we can put in here, which is also equal to the radius multiplied by the rotational speed, if we want. So basically this expression is the full expression that describes the behavior for one nozzle. So this is for one. So for all, it would just be 3 times that. And so that allows us to look at these end-member cases. So you can plug and chug. You can see also that the working in the book ends up being exactly the same as this. But the end-member cases, we're still doing okay for time. So we said two conditions. The first one they do in the book is for it clamped. So the clamped is the velocity of the control surface is equal to 0. And the question is, what is the torque? So if the velocity of the control surface is 0, I'm going to write on this, then I'm going to erase, well, if this is 0, then T theta is just equal to 3 times R. You can substitute this Q over 3, 1 over A2, cosine theta, plus 0, Q rho over 3. Perhaps I don't need to substitute this. But the point is that as this number goes to 0, this becomes a maximum. And you can calculate what the torque is that's applied to hold it in place. That torque means it's going at no velocity. And so the power, if we wanted to calculate it, would be equal to the torque times, well, not times, times the rotation. The rotation, because the velocity of the control surface equals 0, is 0, and therefore the power is 0. The other condition is when the torque that you apply is equal to 0, and then the velocity of the control surface, we could calculate it. And if that's the case, then if this is equal to 0, then the only way that we can get this to be 0 is if the sum of these two components are negative, the inverse of each other. There's certainly a finite flow rate that's coming out of the system, and so the only way we can do it is if W2 theta is equal to minus VCS. And so, of course, that means for our particular geometry, I'll draw it here, W2 is spinning in this direction, and so the negative of that means that, oh sorry, not spinning, means it's pushing in this direction, so the net result is that the rotation that results is a negative net. And so it's not dissimilar from the decapitated gas cylinder, or the vane for that matter. If you hold it in place, you get the maximum force when the velocity is 0. Actually, you get an even larger force if you pushed it against the jet. And in the case where you allow it to go free, it'll actually go at the same velocity as the stuff that's squirting out. The velocity in the direction tangential to this, because this term here has this cosine term that's attached to it. Right? So it's the direction attached to it. And you'd find exactly the same thing. If you plotted now, since for this particular case, if you worked out what the power is, which is equal to the torque multiplied by the rotational speed, since this is equal to 0, this now is 0, even though this is finite. So the work that's done, the power that's output from this is 0. And so if you plotted, again, I've run out of a bit of space, but I could plot it here. If you plotted, for instance, in this, analogous to what we did before, we plotted before force versus velocity of the control surface. If we now plot torque against the velocity of the control surface, we get something like this, where this is equal to W2, etc. And then if you look at the power that's generated from that, from the same arguments that we used before, we'd end up with something that looks like this, where we have a maximum power here. At these ordinates, we get no power generated at all, static, even though there's a big force, and moving at the speed of the sprinkler, but no force applied against it. High velocity but no force. So this is high velocity and no force. This is low velocity and force. Yeah, this is zero velocity and finite force. This is zero force and finite velocity. And we have those behaviors. Okay? So hopefully that makes sense. I tried to make the point that when we look at rotational behaviors, it really isn't very different from the linear system. It's just that it's on this big lever arm, which as r goes to infinity, it actually becomes just a linear case in itself. This is useful to us because it allows us to take a directional force and convert it into rotational force, which of course has use for us in terms of generating electricity. Okay? That's it for me. Okay.